Hello everyone, my name is Anudh Mishra and I am a MBBS student at AIIMS Bhuvneshwar. Today we are going to continue our chapter equilibrium, which we were doing last time. So we had finished with chemical equilibrium, physical equilibrium. Today we are going to start revising ionic equilibrium. So as usual, we'll first finish the basics, the basic formulae and the basic concept. We'll quickly wrap it up. After that, we'll start solving the previous year questions of JEE-Mains. A few previous year questions we'll solve and see how to basically answer a ionic equilibrium question. Okay, so let's start. So starting initially with the definition, like first example which NCERT gives you is the equilibrium between these ions. This ferric ion, then thiosulfate ion, thiocyanate ion, and between your ferric thiocyanate. Okay, this is a good example of an equilibrium between ions. There are numerous examples, and the application of the ionic equilibrium concept is very vast. And this is a bit more, you need to do a bit more calculation in the questions involving ionic equilibrium. So we will start with basics, acid, bases, and salt. Okay. So what are acids? What are bases? What are salts? So acids are what? Sour substances. Acid has been derived from the Latin word acidus, which means sour, and they are turned blue litmus to red. Okay, first thing, and they liberate dihydrogen on reacting with some metals. Now, bases known to turn red litmus blue, they are bitter. They are soapy. Okay, right. What are salts? When acids and bases are mixed in the right proportion, they will react with each other to give salts. So yeah, these three compounds, we know the basic stuff. We have been studying about them since long time. So we'll skip the rest of the small definitions. We'll directly move to Arrhenius concept of acids and bases. Okay. So I hope all of you know the ionization and all, what is strong acid and strong base. Otherwise, I'll tell you a little bit later. We'll start with Arrhenius concept. What does Arrhenius concept say? It says that acids are those substances which dissociate in water to give hydrogen ions, and bases are those substances which produce a hydroxyl ion in aqueous medium. Okay, and they have given a ionization process of an acid. Similarly, ionization process of a base also they have given. They have described a bare proton, the H plus ion. Okay, reactive, freely exists. It bonds to the oxygen atom. Okay, this is really reactive. It cannot exist as H, cannot exist freely as H plus, so it bounds to an oxygen atom of a water molecule, and it gives a hydronium ion. So this is basically introducing us to the hydronium ion H3O plus, which is how your hydrogen ion exists, your acidic proton exists in aqueous solution. It cannot exist as H plus, so it exists with a water molecule, and it is called H3O plus. So they are using H plus and H3O plus interchangeably. Similarly, base liberates a hydroxyl ion. Okay, the limitation which we need to remember. Okay, you need to remember limitation of all the concepts in chemistry. Okay, that will help you in solving some simple questions which you won't be able to solve if you don't remember. So don't lose those easy marks. Try to remember the limitations. It's not that tough. For Arrhenius, the limitation is it is applicable to only aqueous solutions, and it does not occur for the basicity of substances like ammonia, which do not possess a hydroxyl group. These two limitations try to remember. And yeah, see, there are some bases also which do not have hydronium ion. It is not necessary that OH minus ion they have to liberate in order to be called bases. For example, your NH3 and even NR3. What is NR3? R is any alkyl group. These are bases. Okay, they show basic characters. If you ask me, NR3 is more basic than NH3, but none of them release OH hydroxyl ion. So according to Arrhenius, you cannot say that they are bases, but we have seen their basic nature experimentally. It was proved. That is why this has been called a limitation of Arrhenius concept. Okay, they have given a short note on hydronium ion. You can see how an H plus, suppose this one, is bound to your water. See, this is the water molecule to which this H plus is bound to, inducing a positive charge, and the other water molecules are merely attracted to this water molecule because of your hydrogen bonding, right? This is how you can explain the existence of the hydrogen ion. Okay, this is not the only hydronium species. There is H3O plus, there is H5O2 plus, H7O3 plus, H9O4 plus. Okay, similar are also existing. The second concept, which is a bit advanced than the Arrhenius, is your Bronsted and Lowry acid bases. So, what is the definition of acid according to this concept? A substance that is capable of donating a hydrogen ion. For bases, they have said it is a substance capable of accepting a hydrogen ion. So this is a bit different. No releasing. They are not concerned with releasing hydrogen or hydronium, anything like that. They are basically concerned with donating and accepting a hydrogen ion. What does it mean? Let us see a example of dissolution of ammonia in water, and let's see what an acid and base is according to Bronsted and Lowry. So ammonia and water mix to form ammonium ion and hydroxyl ion, right? So you're basically what is happening, and water is giving a proton to ammonia, turning it into ammonia, and water itself is turning into hydroxyl. So the one which is giving the proton is acid, the one which is accepting the proton is base. This is a very simple example. The previous limitation was, I think it has been overcome here. Okay, although still in aqueous solution, but substances like ammonia, for whom you cannot say that they have hydroxyl ion, their basicity is being accounted for just by saying that they are accepting the hydrogen ion from water. Okay, the solution is made basic due to the presence of hydroxyl ion. So this also explains why an ammonia solution in water, an aqueous solution of ammonia, is basic, because of production of hydroxyl ions. Okay, these molecules are called Lowry Bronsted acid and Lowry Bronsted base. Okay, right. The important concept which Lowry and Bronsted introduced was, if you just reverse the reaction, then the roles will interchanged, and if you inverse the reaction, what will be the reaction? NH4 plus OH minus. They are in equilibrium with your ammonia, aqueous, and H2. So who is giving the proton now? Ammonium ion is giving a proton to hydroxyl. So hydroxyl is accepting, so it is a base, and ammonium is donating, so it is an acid. It is very simple. Okay, it is universal and really simple to account for acidity and basicity using this concept. So it is definitely better from your Arrhenius concept. It has explained the shortfalls of the previous concepts. They have introduced a term called conjugate acid-base pair. So what does conjugate acid-base pair means? Looking at this example, ammonia itself was a base, water was an acid, but the ion generated from ammonia, which is your ammonium ion, it is an acid, and the ion generated from water, which is the hydroxyl ion, it is behaving as a base. So this acid base pair, ammonia and its ion, is called a conjugate acid base pair. Similarly, the water and hydroxyl ions are called conjugate acid base pairs. So all the acids have a conjugate base, all the base have a conjugate acid, all the conjugate bases have an acid, conjugate acids have a base to which they can pair. Okay, this is what the concept is saying. If you reverse the reaction, the terms change. And the ones which are related are known as conjugate acid bases. Very simple. They have given an example. Again, one more example with ionization of hydrochloric acid. See, the conjugate base of HCl, HCl which is behaving as the acid, has chloride ion as the base, conjugate base. But H2, which is acting as the base here, its conjugate ion is acting as a conjugate acid. Okay, so acids will always have a conjugate base, bases will have a conjugate acid. Reverse. Okay. Here, have you noticed that water is acting as both acid and base? Okay, see, in the first one, water was acting as an acid, but in the second example, it has acted as a base. So yeah, water has a dual role. We'll come to these substances which show dual role also. For now, let's move on to your Lewis acids and bases. So your Lewis defined an acid as a species. So what? See, they have not told any limitations for your Bronsted and Lowry, but even Bronsted and Lowry had some limitations. Some species, suppose like there are some species, there are some acid-base interactions in which there is no transfer of proton, like H plus transfer absent. There are some species in which there is no proton transfer. Still, we are calling them an acid-base reaction. So what? How do you account for them? You can't account for them using Bronsted and Lowry concept. H plus is not involved. There are some examples like this also. So this is a limitation that although they explained almost all the reactions by giving the concept of donation and acceptance of a proton, the acid-base reactions which did not include a proton, which did not involve a proton, could not be accounted for using Bronsted and Lowry concept. Yeah, they were pretty close, but they associated the transfer of, like, they associated proton. It was kind of wrong. They were really close. Something was being transferred between an acid and base, but it was definitely not a proton always. What was it? Yeah, it was a lone pair. Okay. So Lewis came and defined an acid as a species which can accept lone pair and base which donates a lone pair. This was the missing link in your Bronsted-Lowry concept. Arrhenius is very old by this time. Arrhenius is obsolete by this time. You need not worry about Arrhenius. But yeah, between Bronsted and Lowry and Lewis, this is a very simple yet significant difference which we have to acknowledge. Example they have given BF3 and NH3. Here BF3 is the accepting the electron pair, so it is kind of an acid, Lewis acid. It is called a Lewis acid. And NH3 as a Lewis base. In general, electron deficient species can act as Lewis acids, while electron rich species can donate a pair of electron and act as Lewis bases. Examples you can learn. Let's move on to ionization of acids and bases, and let's introduce this ionic product of water. Okay. So ionization of acids and bases, simple. This is how the reaction basically works. An acid is there, a base is there. You will get a conjugate acid and a conjugate base. Done. We move on to this concept. The stronger acid donates a proton to the stronger base. Right. Stronger acids have the most important concept that you can take back from this para is this. Stronger acids have very weak conjugate bases. So if this acid is really strong, then this conjugate base is really weak. And if it is weak, it can't accept, can't donate lone pair, can't move in backward direction. If it can't donate our lone pair, then in this direction reaction will not move because the base is that weak. So definitely majority of the reaction will be forward only. No backward reaction will be observed easily, which proves that your acid HA is strong if it has a very weak conjugate base. Done. Moving on, the ionization constant of water and its ionic product. For water, we have defined its ionization, we have defined its ionic product, which we need to remember. So this is the equation for ionization of water. The dissociation constant, as we had done in chemical equilibrium, it is represented by this here. There were chemicals there. Here we just put ions instead of chemicals. Nothing much of a difference. The only thing is there is a new constant for water, which is called the ionic product of water, and it is equal to this. So what you have done is, to your dissociation constant, you multiply the dissociation constant by concentration of H2O, okay, and you create a new constant called Kw. The value of Kw for water at room temperature is 10 to the power minus 14, and this value of Kw is temperature dependent as it is an equilibrium constant. Now, from the value of Kw, we can find out the concentration of H2O. It is 55.5 molar. You can find out the dissociated to undissociated water or degree of dissociation of water using these two. This is your degree of dissociation of water. Then you can distinguish acid, bases, and neutral solutions by this formula. This is really simple. If your hydronium ions are more than concentration of your hydroxyl ions, it's an acid. Basic solution has higher concentration of hydroxyl ions. Then your hydronium ions and neutral solutions have an equal concentration. Okay. pH scale. How to find out pH? The basic formula of finding out a pH is this one. pH is negative of log of concentration of H plus. For water at neutral, this is the pH. Because from pKw we can find out if it is a neutral water, then H plus will be equal to OH, which will be equal to 10 to the power minus 7, and log of 10 to the power minus 7 is 7. So neutral water has pH 7 at 298 Kelvin. Now we can define acid and bases and neutral solutions with this pH definition. 7, more than 7, less than 7. 7 is neutral, more than 7 is basic, less than 7 is acidic. Really, really easy. They have formulated one more formula using this basic formula of ionic product of water, which is pKw is equal to pH plus POH, and all of it is equal to 14. This is one more important formula which we need to remember. We'll use them in lots of questions, right? So, how do you measure pH? They've given a kind of two apparatus. There is litmus paper and pH paper, right? For pH paper, you have different colors, 4 strips, so that you can differentially narrow down the pH using whatever colors these 4 strips are giving you. And you can narrow them down using your pH paper. Okay. The next topic is ionization constants of weak acids. How do you find out ionization constant? Using the same concept as your chemical equilibrium, you can find out the ionization of constant of and during an ionic equilibrium constant. So just write down the reaction, initial concentration, assume extent of ionization or degree of dissociation as alpha. Write down the final concentration which you expect. Definitely you will ignore, or you will try to say that the concentration of water will not change because it is a liquid, and it is basically the medium also in which the reaction or ionic reaction is taking place. So you will assume the concentration of water to be same, and you will basically ignore water in your equation. Okay. So for formulating the equation, this is going to be your equation, and this is going to be the formal equation. Both of these equation you can, you either you can remember it, but I prefer you always follow this step and then come to your dissociation constant. Of course, this is a monobasic acid, so you can use this formula for all the monobasic acids. But if dibasic, tribasic acids come in the question, then this formula will not be valid for them, as we will see. Right now, let's define Ka. Okay, at a given temperature, of course, Ka is measure of strength of acid HX. Larger the value of Ka, stronger the acid. Ka is dimensionless, with understanding that the standard state concentration of all species is 1 molar. So these are a few things about your ionization constant of weak acid. You don't need to define ionization constant of strong acids because they dissociate 100%. There is no equilibrium basically in strong acids, right? So in ionic equilibrium, we will be dealing with weak acid or bases and salts, even salts which do not 100% ionize. Why? Because if a substance is ionizing 100%, then it is only existing as ions. Completely, the reaction is moved to this state. There is no existence of the parent molecule, and it cannot be an equilibrium. It is an irreversible reaction. So you don't take strong acid bases and soluble salts also. Moving on, they have given ionization constant of some weak acids. You don't need to remember. They'll give you in question. How to evaluate the pH? pH is, see, pK, they have defined 1 pKa in terms of log Ka. How to find out the pH? First, identify which is the acid, which is the base. First, then write balanced equations. Okay. Then the reaction with a higher Ka is the primary reaction. Enlist in tabular form the following values for each of the species. Okay, initial concentration, change in concentration. Okay, alpha you have to use equilibrium concentration. Then you have to write down the expression for equilibrium concentration and equilibrium constant. Solve for alpha, find out alpha, calculate the concentration of your hydrogen ion, and after calculating the your concentration, you can directly find out the pH. Examples we will see in the as previous year questions. Similarly, there is ionization of weak bases in which Ka is replaced by Kb, and again you have to ignore water here. This is the final expression which you need to remember. This one is basically the same because it is a monoacidic base. That was also monobasic acid. So both of them have similar expression in terms of degree of dissociation. Yeah. Once again, I don't recommend you to learn these formulae. Try to derive them yourself. The expressions for Ka and Kb. Okay. One more example they have given is this ammonia. pKb they have defined as minus log Kb. Similarly, you can find out POH also using the same steps as mentioned in the above equation. Now, what is the relationship between Ka and Kb? the relationship between Ka and Kb is this. Okay, Ka and Kb, if you multiply both of them, it is equal to Kw. pKa plus pKb is equal to pKw or 14 degree. I'm so sorry, not degree. At 298 Kelvin. So these two formulae you can remember. This is the this is defined for the same your chemical. Okay, for if you are calculating pKa for HCl, then pKb is defined for the conjugate base of HCl, which is chloride ion. It is not defined for any other base or any other conjugate base. Okay, this is only valid for a conjugate acid base pair, the pKa and pKb wale formula. Okay, this you need to remember. Don't confuse it with different acids bases, different conjugate acid bases. You should not do that mistake. It is invalid for different conjugate acid and bases. Then see how the Ka expression, the ionization constant expression will change for di and polybasic acids and bases. I told you here there will be two Ka, Ka1 and Ka2. Okay, Ka1 is for the dissociation of first H plus, Ka2 is for the second H plus, and there is relationship between this Ka and K1 and K2, that Ka1 is usually higher than Ka2. Okay, Ka2 is lower, so the dissociation of the second proton from acid is difficult, much more difficult than release of the first proton. This is evident by the value of Ka1 and Ka2 in this table for the same substance. Even they have given Ka3 for some substances. So that is why I always tell you derive your expressions then and there. It is usually better that way. Factors affecting the strength of acid. So the factors are the strength and the acidity basically depends on strength and polarity. Okay. There are lots of factors directly proportional to size here, electronegativity here. So you have to read them up in your inorganic chemistry and organic chemistry. Basically here we just tell you that the strength and polarity depend. They result in how much acidic or basic your compound is. Common ion effect. What does common ion effect mean? It means that if there is a it can be defined as the shift in equilibrium on adding a substance that provides more of ionic species already present in the dissociation of equilibrium. So it is based on Lee-Chatelier. See what is happening if there is a common ion present in the solution. Suppose these two are existing in equilibrium in the same solution. The common ion is there. Then addition of acetate ions to the acetic acid results in decreasing the concentration of hydrogen ions. And if H plus ions are added from external source, then also it moves backward. So this is your acetic acid ka equilibrium. Okay. And if you add H plus, suppose your acid HA is getting dissociated to H plus and A minus, you are adding more H plus in the solution. So you are increasing the product, so reaction will go backward to decrease this thing and maintain the equilibrium. So more HA will be formed. So if H plus is present already in the solution, the common ion effect will be shown. Dissociation will be prevented. This is what happens in common ion effect. The acidity, the amount of dissociation which we were expecting, it is not going to be seen. And there is equation also. You have to calculate this equation also. Like here, there is the concentration, initial concentration is 0.05 molar. And here, you have to calculate pH after deriving your own formula. Then comes hydrolysis of salts. just as I told you, the salts which we consider are salts of weak acid and strong base, strong acid and weak base, and weak acid and weak base. So one thing should be weak, which will act as the thing which is going to be hydrolyzed by water. And the formula which you need to remember is pH is this. Similar formula for buffer solutions. Buffer is basically, the formulae are similar here. Okay, here. This is for buffer, and it is called the Henderson-Hasselbalch equation. For base, you have this one. Okay. For sparingly soluble salt, you define the solubility product. Okay. This was all about your this thing, your buffer and similar concepts. Salt hydrolysis, remember this formula. Let us see thing a few important things about salt hydrolysis. First, we saw buffer. Second is KSP, solubility of saturated solutions. This is an example of a sparingly soluble salt, BaSO4, in water. Okay, equilibrium constant is given by this. So KSP is defined as, because barium sulfate is in excess, it is going to be in excess because it is like less soluble. So more of it will be present as the solid precipitate. So we just, define a new term, multiply the ionization constant by barium sulfate, and you get a new term called solubility product or solubility constant. This is the formula of solubility constant. What is solubility? Molar solubility is the concentration which is present in the solution. Solubility is defined as S. It is basically the concentration only, and S you can easily calculate from the KSP expression. Just keep in mind the coefficients. Okay, keep in mind the stoichiometry. Okay, stoichiometry is really important. For some, it can be 3s, 4s, 2s, 1s. You have to remember the stoichiometric coefficients and multiply everything according to it. Great example they've given here, a small and interesting example. Just see how its solubility product is found out and how they have found out S. Just go through it, appreciate how they have done it. Sorry for the delay. Let's continue with the common ion effect on solubility of ionic salts. Just as we had seen in the previous equation, how can we define the common ion effect here? The thing in common ion effect is it moves the equilibrium to one side, and this condition of not established equilibrium is defined by QSP. KSP is at equilibrium only, and QSP, you have to satisfy two equilibria here when you are having your common ion effect. Okay, and this is the formula which you need to remember. The solubility ka formula, you basically ignore some kind of you take some kind of assumption that there has to be some assumption of ignoring a few points, like ignoring the concentration of the one ion, common ion, which has dissociated from your salt or whose hydrolysis has been done. Otherwise you cannot basically find out, it is going to be too complex. So you have to ignore some this thing, solubility, And because solubility is really low, so S square is basically 2s kind of. You can just assume S square as 2s. Okay, so you have to see how much you can ignore. Just ignore the lower amount if it is being squared, right? Let's move on to the questions of ionic equilibrium, previous year questions. Let's see what we have. The first question asks us 20 ml of NH4OH. This must just mix with 40 ml of this thing. They have to find the pH of the mixture. Let's find out the number of equivalents. Okay, this is a weak acid and weak base. Okay, and the equation is something like this is a strong acid is your H4Cl plus H2O. Okay, this is a strong acid, weak base, salt. Okay, which one of them is in excess? Let us find out. Definitely we can see that the concentration of NH4OH is more, right? And all HCl will be consumed in the reaction because it is a strong salt, a strong acid. Let us find out the equivalents initially. 0. For this it is 2 milliequivalents. For HCl it is same. So we are seeing that they are equal in your concentration, and if they're equal, all of this will be converted into your salt. Of NH4Cl is present in the solution. Definitely H2O will hydrolyze some of it. There will be some salt hydrolysis, and we can find out this thing from pH is equal to 7 minus pKb. Okay, and 7 minus what is your pKb? Kb is 10 to the power minus 5. pKb is 5. It is most 2, but you have to add the contribution of your concentration. Once see the solution once. This is the reaction, and from here they are trying to find out the concentration of ammonium ion. This is the concentration which they find out of ammonium ion in the salt. pH they have applied 7. I just forgot one small term, minus half log C. 7 minus pKb by 2 minus 1 by 2 log C. So 7 minus 2.5 minus 1 by 2 into the log of C they have found out as 1 by 30. So log 1 by 30, and the value is 1.48. So we can easily calculate the pH using this formula. So I had just forgotten one small thing. Okay. The answer is, as we saw, 5.2. Next, class students were asked to prepare 1 liter of buffer solution. pH is 8.26. pH is 8.26. And the amount of ammonium chloride which he needs to dissolve in this much amount of ammonia solution to make 1 liter of the buffer. The amount of buffer they have given 1 liter. pH they have given 8.26, which is pK. They have given pH and the buffer is involving a base. Okay. So we should take basically pKb is there and pH. So we'll just reverse we'll find out the pOH is equal to pOH. How much is pOH here? 14 minus 8.26, that is 5.74, right? 5.74. So pOH is equal to pKb, which is 4.74 plus log conjugate upon base, the concentration. Now the amount of ammonium chloride which the student must dissolve in this much of ammonia solution. They have already given you the concentration of the base, which is ammonia solution. So so we'll just subtract this. This is 1 is equal to log C by B. So yeah, this is coming that concentration of the conjugate acid is equal to concentration of the base. And the concentration of base they have given 0.2 molar. So concentration of conjugate acid will also be 0.2 molar. They have to make a 1 liter solution. How many moles they will add in a 1 liter solution for a concentration of this thing to be 0.2 molar? 0.2 moles. And ammonium chloride 53.5 into 0.2. Oh, I'm really sorry. There has been a calculation error here. If some log is 1, then this value is going to be equal to 10. So 10 C is equal to, so 10B is equal to C. So concentration of conjugate acid is equal to 10 times the concentration of your base. So 10 into 0.2, that is 2 molar is the concentration of conjugate acid, that is NH4Cl or the salt. Okay, conjugate acid or salt, anything. Now 2 molar, for making a 2 molar solution you have to put this much amount of salt. Okay, we're done with the second. Let's move on. Solubility of CaF2 is this much. Solubility product we have to give them. Let's write the equation first. Calcium CaF2, and if it dissociates it will give Ca plus 2 and 2F minus. Let's assume that solubility is S, so this will be 2S. Okay, and this is some value. We have to find out KSP, right? The solubility they have given as S. KSP is going to be equal to S into 2S ka whole square, that is 4S cube. S they have given 2.34 into 10 to the power minus 3 gram in 100 ml. So let's find out because KSP you have to give as in your in terms of the concentration should be in terms of molarity. So we have to find out the molarity first. Let's find out the molarity. 2.34. We'll find out how many moles are dissolved in 100 ml. 2.34 by 78. This much moles in 100 ml. So this much moles in 1 liter. And this is also the molarity. Okay. Now this molarity is the solubility. So KSP is equal to 2.34 into 10 to the power 2.34 into 10 to the minus 3 tha. 2.34 into 10 to the power minus 3 into 10 divided by 78, the whole cube, and has to be multiplied by 4. On calculating this, let me calculate it and I'll tell you the exact answer. So this is basically 10 to the power minus 2. We take this as 4. 4, 3, 4 into 27 into 10 to the power minus 12. So 1, answer is 1.08 into 10 to the power minus 10. This is the answer. This is the value of Ks. Next, they have given a pH metric titration of weak base versus strong acid. So initially, when you are at the equation goes something like this: NH4OH plus HCl, and you're getting salt, NH4Cl plus H2. So till there is you are adding H2O HCl, your pH will, you're adding drop by drop HCl, your pH will keep on approaching the value of 7. Okay, pH will keep on approaching the value of 7 gradually. At a point, after a point, it will go less than 7. So yeah, this is your answer. Such drastic changes will not be seen. Going for the next question, Ka for butyric acid they have given us this much, and pH of this much solution of butyric acid they have asked. Let us assume butyric acid is a monobasic acid. It is a monobasic acid. So for monobasic acids, this is the acid, and this is your equilibrium, H plus A minus. This is C alpha, C alpha, C alpha. Ka is equal to C alpha square upon 1 minus alpha. Assuming that degree of dissociation is alpha. Ka they have given already. Solution they have already given. As you can see, the Ka is really small. So 1 minus alpha is negligible, equal to 1. So alpha is equal to the root Ka by C, and we know the concentration of hydrogen ion is C alpha. So C alpha is equal to this, which will be equal to root Ka into C. So H plus the concentration, let us find it. Ka is 2 into 10 to the power minus 5. Concentration is 0.2, or 2 into 10 to the power minus 1. This gives us 2 into 10 to the power minus 3 molar. So pH is 3 minus log 2, that is 2.7. This is going to be the pH. The solubility product of lead sulfide is this. Then the solubility product of lead sulfide in, the solubility of lead sulfide in pure water is X into this. They have given KSP. Lead sulfide, if it breaks down, it will break down as lead plus sulfide like this. Okay. And this is going to be the solubility. The solubility product is 8 into 10 to the power minus 28, which is equal to S square. So solubility is equal to 2 root 2 into 10 to the power minus 14, because we'll under root this, and root 2 they have given 1.41. So 2.82 into 10 to the power minus 14 is the solubility. Going to the last question. We have some more question, don't worry. 200 ml of this much HCl is mixed with H2SO4. The pH of the final mixture is. We have to find out for pH. Remember, always find out concentration of H plus. Do not just add equivalents of H plus and find out the pH. Okay. First step, how many equivalents of H plus are there? So some 200 into 0.101 plus 400 into 2 into 0.01 again. This will 2 plus 8, that is 10 milli equivalents. Now to convert it into your to convert it into your concentration, you have to divide it by the total volume, which is 600 ml. This comes as 1 by 60. This is the concentration of HCl, H plus, and you can write this as 6 into 10 to the power minus 1, and taking log of this 6 into 10 to the power minus 1, you will get 1 minus log 6. Okay, 1 minus log 6. Log 6 is almost equal to your 1.78, right? Got it? Okay. Next, we move on to the 2023 January attempt questions. First question says dissociation constant of acetic acid is X into 10 to the power minus 5, and this is mixed with the pH of resultant solution was found to be 5. What is the value of X? So yeah, they have made kind of a buffer, and buffer, the concentration is equal. So pH should be equal to pKa. Therefore, if pH is 5, then pKa is 10 to the power minus 5. So X is equal to 1. Moving on, pKa of lactic acid they have given, then pH of calcium lactate solution. This is also a question of a buffer, 0.005 molar calcium lactate solution. The answer is lactic acid, right? If the salt is being formed, it is a strong base, weak acid, strong base salt. Ka is defined. pH is going to be 7 plus 1 by 2 pKa minus 1 by 2 log C. So sorry, plus 1 by 2 log C. 7 plus pKa by 2 is 2.5, half of log C. Log C is 5 into 10 to the power minus 3 a log, that 2 divided by 2. 5 minus, sorry, 3 minus log 5. Log 5 is 0.7, so 2.3 divided by 2, so 1.15. This is something like 10.65 is the pH, or 11, you can round off to the nearest integer. Next question is liter of buffer solution contains 0.1 mole of this and this. This is again a conjugate acid base pair. You add HCl by dissolving gaseous HCl. pH of the solution is found to be. So if 0.01 mole of each is there, therefore the concentrations are equal. Okay, and you have added some amount of HCl. So some more salt is going to be. So 0.12 mole of salt will be found, and 0.08 amount of acid will be left, because some base will react with your acid. So this is, you take the log of this, and pKb is equal to POH. Right, pKb they have given as 4.745 plus log, this is 2 by 3, log 3 by 2, that is log 3 minus log 2, and it is basically 0.17. Okay, 0.17 and 4.915 is the POH. Subtracted by 14, this comes as 9.085. This is the pH of the solution. Okay, this is going to be the last question. When hydrogen ion concentration changes by factor 1000, pH changes. Why? So hydrogen ion, suppose increases by 1000, you multiplied by 1000, pH will definitely decrease by 3 units. This is really easy. We can do one more. Aniline, ethanamine, and ethyl ethanamine, and then diethyl ethanamine. This is pKb. The lower the pKb, the stronger the base. So I'll give the enamine, right? This is an N-diethyl. This is an N-diethyl ethanamine. This is N-ethyl ethanamine. This is just ethanamine, and this is NH2. So yeah, aniline is the weakest. You'll learn this in organic. Don't worry. The strongest one is this, followed by the option. Sorry. Two. This is a basically like exception in your organic, so it comes as 2 3 1. So secondary, tertiary to primary. Which one is secondary? This is secondary, this is primary, this is tertiary. So C will be given second, C will be 2 3 1. So this is, I think this is the correct answer. Okay, yeah, this will you'll study in your this thing. So yeah, we're done with the chapter, and all the best guys for your JEE mains. Thank you.